All right, so looks like we have a late arriving crowd today. That's okay. Maybe they'll join us shortly. Um, First thing before we get going, another reminder. I'll remind you every day this week, but our first test coming up Monday, uh, 11 a.m. We'll go up through section 3.7. We should finish that up, section 3.7 tomorrow on Thursday. On Friday this week, we'll take first half class, talk about some new stuff. The second half class, we'll talk some more about the tests or sort of a review, if you will. So today we're going to continue talking about material properties, stress strain diagrams. That's where we stopped yesterday. So sort of quick review reminder. What a typical stress strain diagram would look like for a steel. We have a linear region where the graph is linear, it's a straight line, and then it will start to curve. Usually it'll curve over and then kind of flatten out for a little bit and then go up, and then eventually at some point the material fails and breaks. Again, this is a typical shape you would find for most steels. Again, depending upon the alloy of steel, the numbers will be different, but the shape will be similar. And we talked about some particular significant stresses here, like the proportional limit that defines the linear region, yield stress, ultimate stress, fracture stress. So just to make clear, as far as on a test goes, what I would expect you or hold you responsible for is if I gave you a stress strain diagram like this and ask you, what's the value of the yield stress? What's the ultimate stress? You should be able to look at that stress strain diagram and identify those. Okay, is everybody clear with what's expected of you to know about stress strain diagrams? All right, well, the first thing we're going to talk about today is a little bit, and we're not going to spend much time on this, is what if we have different types of materials? How does the stress strain diagram change? Like again, I said this is the shape you would find for most steels, but in the next section in your book, which is section 3.3, which I highly encourage you read through this. There's some good information in there, but it talks about what stress strain diagrams look like for different types of materials. So in other words, if you had a material that was say very ductile, so if you had something that's very ductile, an example might be to some extent aluminum. Aluminum much more ductile than steel. Right? It stretches a whole lot easier. And for these type materials, you don't get this well-defined linear region. It pretty much is curved from the beginning, and it will just kind of maybe look something like this, and eventually you'll have failure. So very different type shape diagram you would get for something very ductile compared to a steel. Also, in this same section, it talks about if you had like a very, very brittle material. So if we had something that was, let's see, very brittle. I assume everybody knows what brittle means. For example, something like glass. Glass doesn't deform much. Maybe a ceramic, same type thing. So you get very little actual deformation. And what your stress strain diagram turns out to look like is it's, for the most part, all linear, and it is very steep. And that's supposed to be straight line, and it breaks. Right? You don't get a lot of deformation. Glass doesn't stretch very well. Ceramic doesn't stretch very well. When it starts to deform, it's going to break shortly thereafter. Right? So that just kind of gives you an idea of, comparatively different types of materials compared to steel. Any question about that? Of course, if you got a real ductile or a real brittle material. All right, well, the next thing then leads us into what's called Hooke's Law. This is in the next section, 3.4. And you're going to see a lot of the formulas that we'll see later on in the course that are developed and used. A lot of them go back to Hooke's Law. Just for example, in say dynamics, so many of those formulas and relationships go back to Newton's second law, F equals ma, where you're going to find a bunch of relationships later that go back to Hooke's Law. And it's actually a really, really simple, easy concept that Mr. Hooke, I forget his first name, obviously came up with this, and now he's famous and got this law named after him. And any one of you could have come to the exact same result as he did. So let's go back to looking at a stress strain diagram. And again, we'll go back to maybe what a typical steel might look like. Right? And we define this. Yeah, this linear region, the stress at that point on the graph is what we call the proportional limit. Well, we have a straight line, so we can calculate the slope of that straight line. So the change in the y direction is going to be the change in stress. The change in the x direction is going to be the change in strain. So again, for the linear region, the slope, right? Everybody knows slope rise over run so it'd be the change in the stress over the change in the strain. And we give that slope a name, and notation wise, we call it E. And actually, this has two different names. Where the E comes from is the name modulus of elasticity. That's where why E is used. You'll also see this called Young's modulus. So either one of those names refer to the same thing. Probably for the most part, I'm going to use this terminology and refer to it as modulus of elasticity. But it is a material property. So E is a material property. Because I said yesterday, each material has its own unique stress strain diagram. So each material is going to have a unique slope to that linear region. So each material is going to have a unique value for E. Units, right? Well, it's stress over strain, and we said strain was dimensionless. So the units are going to be the same as stress. So you would see maybe KSI, or if it's in SI units, probably more likely instead of megapascals, you probably see gigapascals. Just note here, giga is 10 to the ninth. You see very large values. That's for stress in SI units. That's why we typically use megapascals. Well, for E, you're going to get even bigger values, and so typically it's given as gigapascal. In fact, when I'm thinking about it, if you haven't discovered this yet, in the back of your textbook, it's on the inside back cover and on the facing page, there's a table of material properties back there. If you have an electronic version of the text, it is in there as well. If you cannot find it, if you let me know, I can maybe help you locate it. But you also have this table, and so I'll show you. This is, let me turn it this way. And let's see if I can get it to focus. So this is a table out of the back of the book for U.S. units or English units, whichever one you want to prefer to call this. But here you'll see the modulus of elasticity, E. Right? So this column, these are the values for E for these materials that are listed over here. Also, while I got this up here, just point out, here's the yield strength, what we call the yield strength or yield stress. Those are the values of yield stress for those materials listed over here to the side. Ultimate stress we've talked about, right? That's what this column is. It gives you values for the ultimate stress of those corresponding materials. Now, this by no means is a complete list. Obviously, we've got a few materials over there, but there's lots more out there, and there's lots more steel alloys than what are listed here. But also, while I'm thinking about it, I'll mention most of the problems in the book, if you need a material property, most of them are listed in the problem statement, but on occasion you'll run into a problem where they will just tell you the material, right? They'll tell you it's a 2014 T6 aluminum, and you're going to have to refer to this table in the back of the book if you need any of these material properties. So just be aware of that. And part of the reason I mention that is I had a student, I don't know, it was a couple of years ago, came to my office and he couldn't get the answers in the back of the book. And I looked at his work, asked him, well, where did you get these values? I forget what material property it was. And he said, oh, I just looked it up online. And the values in the table he found online were a good bit different than the tables listed in this table here, provided by the textbook. So I mentioned that for your benefit, use these values. Because if you look at a different material property, a source, you very likely will see slightly different values. These are not, worldwide, everybody says E for 2014 T6 aluminum is 10.6 times 10 to the third KSI. You look in a different table, you might find a slightly different value for that. So be aware of that. If you're solving any problems in the book, use these values that are given in the table from your textbook. Any question about the table material properties? Okay, then we'll come back then to what we were talking about. We were headed toward Hooke's law, right? And to get Hooke's law, we define the slope of this linear part as the modulus of elasticity, and we call it E. So all Hooke's law is very simple. It's the relationship between stress and strain. Typically, the way you see it is sigma is equal to E times epsilon. Now, a couple things I'll mention about this. One is this is only valid in that linear region. That's where we got this from, was that we were just looking at the linear part of that stress strain diagram where the graph is a straight line. But to some extent, we talked about this a little bit previously. That's where in the real world your structure is going to be. We're not going to intentionally anyway design a structure that's going to see a stress higher than that proportional limit, or certainly not higher than the yield stress. If you got any kind of factor of safety, you're going to be down here in this linear region. So this is going to be valid for almost every real structure that's built. Now, if you get into what we call non-elastic or plastic deformation, and we get out here in this part, well, this is not true anymore, and you got a whole different ball game. But we're not going there. We're going to stick to this linear region. The other thing, all this is you may or may not recognize this, but it's just the equation of a straight line, right? Remember back in, I don't know, Algebra 1 maybe? Whenever you took Algebra 1, y equals mx plus b. Well, in this case, y, in our graph, y is stress. The slope is E. X is epsilon. This is the y-intercept. And for our graph, the y-intercept is 0. Hooke's law. All you need is Algebra 1 to come up with Hooke's law. So, gives you hope. Maybe there's some simple relationship like this that you can discover or see that somebody else hadn't previously, and you'll get your name on it. Let's see, we'll call it Baggett's law. Not picking on Adam, just his name was at the top of the list over there. So come up with something like this, and your name will be immortalized. Right? But it gives us a good relationship between stress and strain. So as long as we know what the material is, if we know the stress, we can get the strain. If we know the strain, we can get the stress. Right? Because again, E here is dependent upon the material. Right? Any question about Hooke's law? All right, there's one other thing I wanted to mention to you or talk about related to stress strain diagrams, and this is more just some notation, if you want to call it that, the textbook uses that you need to be familiar with. So, for example, let's go back to what a typical stress strain diagram would look like for a typical steel. It'd be something like this. All right. Well, what you're going to see in the textbook, for especially in the problems, it's all motivated for the safe space. But I talk about this because first time, some textbooks do this, some textbooks don't. And when we switched to this textbook, immediately a bunch of students started asking, well, what is this? They didn't understand what the textbook was doing. But basically what the textbook does, in order to allow you to be able to read these values, right? What they'll do is essentially they'll cut it in half. Right? So they'll basically cut this, and you'll have two different scales. So what you'll wind up with, what you'll see in the textbook, and I'll show you a picture in just a second out of the textbook. You'll see something like this, and then you're going to have one set of numbers down here that go with that part of the graph. And then the second part of the graph over here, this part, they'll put on top of that, right, and you'll get a second row of numbers. You're going to get two different rows down here, and I don't know which one's which. We'll see in a second. But I got a picture of what one of the problems in the back of the book looks like, and I'll put that up there in just a second. But the reason for this is if you drew this diagram to scale, this part of the graph over here would be so small, you couldn't really distinguish any numbers. Or if you drew it large enough to scale where you could read the first part of the graph would be so big it would take up the whole page. It would go all across the page, and that's why they do this, so they don't have this stress strain diagram that goes all across the page. So again, this is an example of what you see in the textbook, and I want to make sure everybody knows how to read and interpret this. So actually I had it backwards from what I said a while ago. So what they've done is they've taken this diagram that looks like this, and they cut it in two. And so what you have is this part of the graph corresponds to that part of the stress strain diagram, and these are the smaller values of strain down here correspond to this part of the graph. So if you're in this region, you're looking at this part of the diagram, and these are going to be your strain values. Whereas if you're out here in this part of the stress strain diagram, that's drawn up here above that, and the strain values for that are the larger values here. All right, so you got so those correspond to those numbers, and this part of the graph corresponds to those numbers. All right, but is that clear? Everybody understand? It's actually this is one of your suggested problems. When you look back there and you see this, you understand what they're trying to communicate to you and be able to look at that diagram. Any questions about that? All right. And again, I'm taking silence as everybody's good and understands how to read that stress strain diagram when it's broken up like that. All right. So let's see. Moving along, what we've got next is going to talk about Poisson's ratio. This is in section 3.6. Now, so far we've talked about. Somebody have a question? Okay. That if we apply an axial load to a member, right, it's either going to stretch it or it's going to compress it, right? We're going to get a change in length in the longitudinal or the axial direction. But as well as getting a change in the longitudinal direction, we're also going to get a change in the what we call the lateral direction. All right, so I think a picture here really helps. So say we've got this member, and it's got some original length L. Right, this is undeformed. I can spell undeformed length L. And let's say say that end is fixed back there so it don't move. All right, well, if we apply a force and we pull on this thing, in tension, it's going to stretch. Right? It's going to get longer. So our deformed member, that we apply some tensile force P to this thing, and this is what we're going to call the x direction, longitudinal direction. Right? It's going to stretch some distance, delta L, or I'll just call it delta here, whatever notation you prefer. Now, we've talked about the longitudinal or axial strain, epsilon, longitudinal, or if you like using the x, y, and z notation, this would be the strain in the x direction, right? Is just that change in length, right? So if this would be some length L prime minus the original length divided by that original length, or delta L over L, or delta this way over L, however you want to define that notation-wise. That we've already discussed. Right, but if you notice how I drew this picture, when you take something and you pull it and stretch it, it's going to get longer in that direction. It's going to get shorter in this direction, the vertical direction here. And so if this thing starts out with some height y, again, which would be the undeformed, it's going to shrink, or it's going to get shorter in that direction. Now, the converse is true. If you pushed it in this way and compressed it, it would get shorter in the longitudinal direction, and it would grow and get bigger in the lateral direction. In this case, the vertical direction. Right, and that should be sort of intuitive, right? If you pull and stretch something, okay, it's going to shrink a little bit in the lateral direction. And if you compress it and squish it in, that material's got to go somewhere, and so it pushes out and gets bigger in the lateral direction. So we define what we call the lateral strain as a change in that direction, or in this case, call that the y direction. Just like before, it's a change in length over the undeformed length, or call it delta lat over y. So it's the change in the opposite direction. I have there's a picture in your book. I think I've got it here. So I'm going to show you this picture in just a second. Right, but everybody with me in that if you pull and stretch something in the longitudinal direction, it's going to get shorter in the lateral direction. If you compress it and it gets shorter in the longitudinal, it's going to get bigger in the lateral. In fact, that's what this picture in the book shows, something being compressed. Again, this picture, this is in your book. You can look up page 106. All right, so here's what it looks like. It's undeformed, right? You got the specimen is sitting there, and then you're going to compress it. And you can look and see what happens, right? It gets shorter, it gets fatter, right? It gets wider. And that's going to happen unless you've got some really, really weird exotic material that I'm not familiar with, which that's why I'm going to put the disclaimer. I'm not going to say 100% of the time, but 99 point something % of the time, this is what's going to happen. It gets shorter, it gets wider. You stretch it, it gets longer, it shrinks, gets skinnier. Okay? But anyway, you can go to that page in your book if you want to see that picture in a little more detail, read about it. All right. One other thing before we define Poisson's ratio. So that's where we're headed with this, is define what Poisson's ratio is. My 2D picture here is just showing X and Y. But if we looked at, say, a 3D situation, I can draw straight lines here. And you're going to see pretty consistent from now on throughout this course. The longitudinal, the axial direction, we're taking to be the X direction. The vertical direction, we're calling it Y. And the horizontal direction, if you look at that cross section, we're going to define as the Z direction. As long as the material, if the material is homogeneous and isotropic, which basically these two requirements ensure you get the same material properties in every direction. So as long as we've got a homogeneous and isotropic material, the lateral strain is going to be the same in the Y and Z direction. So the lateral strain is the same in the Y and the Z directions. In other words, the lateral strain, the Y, same as the lateral strain in the Z. Now, that does not say, so pay close attention to this, because sometimes that gets misinterpreted. That doesn't mean the deformation is going to be the same. So the actual change in length in the Y and the Z directions very much could be different. It says the strain is the same, but remember the strain is a ratio of the change over the original undeformed dimension. That ratio will be the same. Okay, is that clear? The confusion there. All right, so finally then, that brings us to what we were trying to define in this section. It's called Poisson's, I think I spelled that right, Poisson's ratio. And here we're, again, continuing our journey through the Greek alphabet. And mine's probably not going to be too good, but this is a lowercase Greek letter nu. Oh, my pen's not right. Nu. Looks kind of like a V that's kind of squashed and deformed, but that is the Greek letter we're going to use to denote Poisson's ratio. Now, Poisson's ratio, is, the name implies, it's a ratio, and so it's a ratio involving longitudinal strain and lateral strain. In fact, if you want a kind of a wordy definition, it is the lateral strain over the longitudinal strain. And if we write it like this, we need to employ absolute value. And again, the absolute value is there so that we always get a positive value. Because go back to our previous discussion, if we stretch it and it gets longer, the longitudinal strain is positive. But the lateral strain is going to be negative, right? If you take the deformed length in the lateral direction minus the original, you're going to get a negative number. So if the longitudinal strain is positive, lateral is negative. And as we saw in that picture a minute ago, if you compress it, the longitudinal strain is negative and the lateral strain is positive. It gets bigger. They're always going to be opposite signs. So if one's positive, the other one's negative. That's why you put the absolute value on there so that you always get a positive value. Now, if you write this out as a formula, nu, Poisson's ratio, we take care of always being positive by putting a negative in front of it. It's the lateral strain over the longitudinal strain. Or if you prefer the X, Y, Z notation, it'd be strain in the Y direction over the strain in the X direction, which is equal to strain in the Z direction over the strain in the X. Again, the negative sign is put in there so that you get a positive number because, again, they're going to be opposite signs. If one's positive, the other one's negative. And this is also a material property. So Poisson's ratio is a material property. Different materials have different values of Poisson's ratio. That's, again, determined very easily in a lab. You would take a specimen like that picture and apply an axial force, measure how far it changes in the axial direction, measure how far it changes in the lateral direction, and plug those numbers in, and you got Poisson's ratio for that material. And if we go back to, let's see if I pull up this table we were looking at a minute ago. You see, if you go over here to this column, Poisson's ratio. And so all these values down this column are Poisson's ratio for those materials. Now, one thing you might notice, if you look at these values, they're all pretty close with one exception. And I have to pick on my civil engineers again. If you notice, all of these values for Poisson's ratio are all between what looks like 0.35, maybe is the biggest, and down to looks like 0.28 maybe, excluding concrete. So that's why I say I'm picking on a civil engineer, because they're the ones that deal with concrete. All these other materials, it's going to be maybe just a little below 0.3 or a little bit above 0.3, but it's somewhere in that ballpark. It's in that range of plus or minus a little bit, 0.3. That's, we learned as an engineer in the real world. If you had a material and you didn't know what Poisson's ratio was, use 0.3 and you would probably be pretty close. But they do vary. Again, from a little above to a little below, but concrete is the outlier. It's nowhere close. It's 0.15. So again, civil engineers, you get to work with the concrete, where the rest of us don't have to deal with concrete. But it's different. Anyway, it's in that table in the back of your book as well, Poisson's ratio. So if you got a problem where you're given the material and they don't give you Poisson's ratio, you can look it up. All right, any questions relating to Poisson's ratio? All right, so we got about 10 more minutes or so. So we're going to talk about one more thing, and then I think that will put us to the point where tomorrow we're going to take everything we talked about today, and tomorrow we'll spend pretty much the whole time solving problems using this that we discussed today. But we move on to one last thing that we'll discuss today. And this you'll find in the next section in 3.7. Here, before you get to the problems, there's some discussion about a shear stress, shear strain diagram. So the stress strain diagram that we discussed previously, and typically if it's just referred to as a stress strain diagram, it's referring to normal stress versus normal strain. But you can have, and you will see, a shear stress versus shear strain diagram. But it's the same concept, but you're plotting shear stress as opposed to normal stress versus shear strain as opposed to normal strain, which we use epsilon. And this, for example, maybe your shear stress versus shear strain diagram. Again, for most steels, it will have a nice linear section, and then it will have a curved section. And so there is what we refer to as the proportional limit, right, that defines this linear part, just like with the other diagram. And remind you, we talked about shear strain the other day, whereas normal strain was change in length over length. Remember, this shear strain was the angle of distortion. So just a quick review. If you've got some element, you put a shear stress on the top and the bottom, right, it's going to deform, and we called this angle of distortion. That was the shear strain. It was in radians. But if you take a specimen and subject it to shear stress, you measure this angle, and that's where you would get these data points. And somebody does this in a lab, and we have the same thing that we came up with for normal stress and normal strain. We had Hooke's law, so we'll call this Hooke's law for shear. So for the linear region, we can define the slope by taking the change in shear stress over the change in shear strain. And that slope we give it a name just like we did before, except here we're going to call it G. And G is called the modulus of rigidity, or it has two names also. You remember E was the modulus of elasticity, or Young's modulus. Here you'll see this referred to as modulus of rigidity, or very commonly called the shear modulus. So either one of those terms are pretty common. I think this book uses the modulus of rigidity. It's a material property, just like E is, because each material is going to have a unique diagram, and so the slope is going to depend on the material, and that's all G is. It's the slope, in which, if I go back to my material properties table here, we should find that as well. Let's see, here, modulus of rigidity, G, is this column. So these are the values for G for those materials. Notice when we get down here, concrete and plastic and wood, they disappear. Those materials aren't good in shear. But for these metals up here, we do get values for, again, he calls it the modulus of rigidity, or G. So that's in that table in the back of your book as well. Right, so just like Hooke's law was sigma equals E epsilon, Hooke's law for shear, likewise, it's just the equation of that straight line, y equals mx plus b. So here, y is shear stress, slope is g, and x is gamma. So this relates shear stress and shear strain. So if you know the material, that's where G is, that's the material property. If you know one, you know the other. If you're given stress, you can get strain. If you are given strain, you can calculate stress. Right? So that's what Hooke's law for shear is used for. And I'm not going to go through and derive this. Actually, it's not trivial derivation. It actually involves some things that we haven't talked about yet. But so I'll just cop out and say also it can be shown, and we definitely don't have time to do it today anyway because we only got a few minutes left. There's a relationship between these material properties that we talked about today, E, G, and nu. The modulus of elasticity, the modulus of rigidity, and Poisson's ratio. All of those are related, and you can come up with this relationship that G is equal to E over 2 times 1 plus nu. Now, this you will find in your textbook. I'm not going to, again, say for 100% sure that there might not be maybe 1 or 2 problems out of the textbook where that might be useful. Not many. I will tell you on the test, there will be no problem that would require you to use this formula. So it's something to be aware of, and you might find it useful occasionally to use when you're working a homework problem. But on the test, you would not need this. Basically, the only place you would use this if you knew 2 of the material properties and didn't know the third one, then you could use this to find the third one. Well, I'm not going to give you a problem like that on test because, well, in the real world, guess what? If you know the material, you're going to go to a table like this, and you can look up all 3 of them. Right? You're not going to know 2 and 1 unknown. And so that's why I'm not putting a whole lot of emphasis on this and don't require you to know this on the test. Okay? Any question about that? All right, so I think that is a good place for us to stop because the next thing we need to do is take all this stuff that we talked about today and apply it to solving some problems. And that's what we'll do tomorrow. So this is a good place to end today's session. So any questions before we stop? And again, in a minute, I'll stop recording. And then, as always, if you've got questions you want to stick around after class and we can talk about, that's fine. But I want to make sure if anybody's got any questions right now, especially about what we talked about today, let me know now before I stop recording. All right, I'm not seeing any questions, so I'm going to stop recording.